So the fourth type of partial fraction resolution is somewhat a combination of the second type and the third type. Over here, you have an entire expression inside a square bracket. So that is where the second type of partial fraction resolution comes in. But also you can see that the expression inside has the variable with a power. So that is where the third type of partial fraction resolution comes in. So how will we deal with this? Well, as you know, we'll have the two partial fractions, one with this term being of the power of 1 and the second one having this expression with the power of 2. As you know, in the second type of partial fraction resolution, this is what you did. You basically had an entire expression inside a certain power bracket. Over here, that's a square bracket. So you'll have expressions in, you'll have partial fractions with denominators in increasing powers of this same expression. So for example, if this was x squared plus x plus 1 whole to the power 3, you would have basically three partial fractions with ax plus b in the first one, cx plus d in the second one, and say ex plus f in the third one. And in the denominators, you would basically have x squared plus x plus 1 in increasing powers up to 3. So now, how will we go about this? Well, as you know, in every kind of partial fraction resolution, you'll basically take the LCM so that the denominators on the left-hand side and the right-hand side will be equal. So ax plus b will be multiplied with x squared plus x plus 1. So that the denominator will also be multiplied with x squared plus x plus 1, and that will end up giving you this. And cx plus d already has x squared plus x plus 1 whole to the power 2, so it will remain as it is. So now the denominators on the left hand side and the right hand side are equal. They will be cancelled out and you'll equate the numerators to each other. Now, what will you do after actually calculating these entire expression, after multiplying this expression with this expression? You basically get this whole equation, and we'll call this equation number 2. Now, you'll simply equate the coefficients of x cubed, x squared, and x on the left hand side and the right hand side equal to each other. So look at this. You basically have only one x cubed expression on the right hand side. There is no other x cubed expression on the right hand side. And there's only one expression of x cubed on the left hand side as well. And the coefficient of x cubed over here is 1. So a is equal to 1. That's as simple as that. Now, the coefficient of x squared on the right hand side is a plus b. So a plus b is equal to, well, there is no x squared expression on the left hand side. So that means that the coefficient of x squared on the left hand side is 0. So a plus b is equal to 0. Now, since we have the value of a already from this part here, we'll plug that in to this part, and so b will be equal to -1. Now, the coefficient of x on the left hand side is 2, and the coefficient of x on the right hand side is a plus b plus c. So a plus b plus c is equal to 2. Now we have the values of a and b above, and we'll plug those in to get the value of c, which is equal to 2. And the constant on the left hand side is 2. The constant on the right hand side is, well, b plus d. So b plus d is equal to 2. And we already have the value of b from before. When we plug that in, you can see that the value of d is equal to 3. So we now have values of a, b, c, and d. So we'll plug those values in to our original partial fraction that we developed, and you'll basically get this. And these are the required partial fractions.